Welcome to the lecture on series solution of Bessel's differential equation. So in this lecture I'm going to describe briefly about how to find the series solution of Bessel's differential equations by using Frobenius method. So first we will see what is meant by Frobenius method. Working rule: consider a second order ordinary differential equation in the form p0 of x y double dash plus p1 of x y dash plus p2 of x into y is equal to 0. Call it as equation number 1. So where this p0, p1, p2 are the polynomials in x. So here to apply the Frobenius method, we have to satisfy the condition p0 of x is equal to 0 at x is equal to 0. It means that in the function p0 of x, if we replace x is equal to 0, the value must be equal to 0, we have to get it. So then only we can able to apply the Frobenius method. So now if this condition is satisfied, so we have to assume the y equation now. So y will be like summation r from 0 to infinity ar x power k plus r. So now to satisfy this condition, we have to differentiate y with respect to x one time to get y dash, and we have to differentiate y twice to get y double dash. So now I'm going to find the value of y dash. So differentiating the given equation y with respect to x, I will get summation r from 0 to infinity. The constant ar I'm keeping as it is. Differentiating x power k plus r one time, I will get k plus r into x power k plus r minus 1. So since the differentiation of x power n is n into x power n minus 1, so this is the same formula I'm going to apply here also. So next is y double dash. So summation r from 0 to infinity ar. So differentiating this again, so I'm keeping the constant k plus r here only. Differentiating this function with respect to x again, I will get k plus r minus 1 into x power k plus r minus 2. So now I'm going to call this equation, this assumed equation as star, and replacing all this y, y dash, y double dash in the equation number, and we have to simplify the equation. So after simplification, I mean after grouping all the terms and taking all the common factor, we have to get one equation here. So after simplification, we have to equate the coefficient of lowest degree term in x to 0. So after simplification, we have to equate the powers of x term. So in that, I'm taking the least power of x term, I'm equating it for 0. So after equating it for 0, I will get a quadratic equation in terms of k, which called as an indical equation. So the roots will be in terms of k1 and k2, I will get it for the quadratic equation. So now in general, if I equate the coefficient of x power k plus r to 0, which results in a recurrence relation, which helps us to determine the constants a1, a2, a3 in terms of a0. So at finally, if I equate the value of coefficients of x power k plus r to 0, I can able to estimate the values of the constants a1, a2, a3 in terms of a0. I am going to estimate. So now I am having the values of the constant a1, a2, a3 in terms of a0. So from the assumed equation y, I am going to expand the assumed equation y. So if I expand that summation, I will get the equation like x power k into a0 plus a1x plus a2x square, and so on I will get it. So now in this one, we have to replace the obtained constant values a1, a2 in terms of a0. So now the entire equation having a single constant, that is a0, I can take the common factor a0. Remaining the polynomial equation, I am replacing it as f of x. So where f of x is an infinite series. And here the condition will be equal like k1 minus k2 will not be equal to 0, 1, 2. So now for the general solution, so the general solution of the equation y will be given like a into y1 plus b into y2. So where y1 will be nothing but a0 into x power k1. Since we are having two roots here, so the one root is k1 f of x, one more root is y2 is equal to a0 into x power k2 f of x, will get it. So now we will see how to find the series solution of the Bessel differential equation by using Frobenius method. The Bessel differential equation of order n is x square y double dash plus x into y dash plus x square minus n square into y is equal to 0 is called as a Bessel differential equation. So where n is a non-negative real constant, we employ the Frobenius method since the coefficient of p naught of x will be here like this. The coefficient of y double dash of x value, that is p naught of x, will be not be equal to 0 here. We can see here the coefficient of y double dash is p naught of x, and this p naught of x is equal to, I got it, x square. So if I replace x square, x is equal to 0 here, I am getting p naught of x is equal to 0. So this is the required condition to apply the Frobenius method. So once this condition is satisfied, we can able to apply the Frobenius method there. So now I am going to apply the Frobenius method. So first let me assume y is equal to summation r from 0 to infinity ar x power k plus r. So as I told that to apply the Frobenius method, we have to find y dash and y double dash here. So differentiating y with respect to x one time, I will get summation r from 0 to infinity ar k plus r x power k plus r minus 1. Y double dash will be equal to summation r from 0 to infinity ar k plus r minus 1 x power k plus r minus 2. So now replace all this equation y dash and y double dash in the equation number 1. We'll get summation r from 0 to infinity ar k plus r minus 1 into x power k plus r plus summation r from 0 to infinity ar k plus r x power k plus r plus summation r from 0 to infinity ar x power k plus r minus 2 minus n square into summation r from 0 to infinity ar x power k plus r. So this equation is obtained like, so now I'm having here y double dash is equal to this equation. Okay, if I replace y double dash in the previous equation here, so here already one x square term is there, so I'm combining this x square term with x power k plus r minus 2, so that this x square term and their x power minus 2 term gets cancelled. I'll get only x power k plus r. Same thing here also. In y dash term, I'm having the power of the x like x power k plus r minus 1 is there. Since here x power 1 is there, I can combine x power 1 with x power minus 1. So I will get x power k plus r. So since y having only x power k plus r term, so if I combine with x square, I'll get the equation like x power k plus r plus 2 here. Since here x square is there, so it will become, adding the power there, I will get x power k plus r plus 2. So now I'm going to group all the equations. So like taking summation r from 0 to infinity ar x power k plus r common factor from all the three terms. So from this term and this term and this term, I'm taking summation ar x power k plus r common factor. I'll get this equation plus summation r from 0 to infinity ar x power k plus r plus 2 is equal to 0. I'm keeping as it is. Call it as equation number 2. So now if I replace r is equal to 0 here, I will get only terms in the terms of x power k here. So here x power k will be the least term. I'm going to equate this x power k coefficients to 0. So I will get a naught k square minus n square will be equal to 0. So this equation is obtained by replacing r is equal to 0 in the entire equation and taking the lowest term, that is x power k will be lowest term there. I'm equating that coefficient of x power k to 0. I got the equation like a naught k square minus n square will be equal to 0. Since a naught cannot be equal to 0, I will take only k square minus n square will be equal to 0. On simplifying it, I will get k is equal to plus or minus n square. So this is called the identical equation or quadratic equation. On simplifying it, I got the roots like k is equal to plus or minus n. So now if I equate coefficient of x power k plus 1 to 0, like if I replace r is equal to 1 here, I'll get x power k plus 1 term. So I will get a1 k plus 1 whole square minus n square will be equal to 0. So I can take here a1 is equal to 0 because I can't equate this k plus 1 whole square minus n square will be equal to 0 because of already I took k square minus n square will be equal to 0. K is equal to plus or minus n. So again if I equate this k plus 1 whole square minus n square will be equal to 0. Both the condition will not satisfy here. So I can't accept this condition. So I can accept only a1 is equal to 0. So I got here a naught is not equal to 0. a1 is equal to 0. So since the roots are k is equal to plus or minus n here. So now I'm going to equate the x power k plus r coefficients to 0. So to get x power k plus r coefficient to 0, I'm going to convert this x power k plus r plus 2 in terms of x power k plus r. By only here I'm replacing r tends to r minus 2, I will get x power k plus r here. So I can equate the coefficient of x power k plus r now. So I will get ar k plus r whole square minus n square plus ar minus 2 will be equal to 0. So ar will be equal to minus of ar minus 2 by k plus r whole square minus n square. With the condition r is greater than or equal to 2 only we can take it. So now already we know the values of a0 and a1. So now start doing with the next values. So first we choose the first case. So I'm choosing the k is equal to plus first root n. So if I replace k is equal to n here, I'm getting the equation like this. ar is equal to minus ar minus 2 by 2nr plus r square. So now from this equation I'm going to estimate the values of a2, a3, a4 in terms of a0. If I replace r is equal to 2, I'm getting the equation like a2 is equal to minus a2 4n plus 4, or minus a2 is equal to 4 times of n plus 1. I can take it. If I replace r is equal to 3, I will get a1. So sorry, I will get a3. So I will get a3 in terms of a1 actually. Already a1 is 0. Obviously a3 will be 0. I will get it. So similarly, all a5, a7 will be 0 because all these odd numbers will be represented in the form of a1. So since a1 is 0, I can replace all this odd number constant will be equal to 0. So a4 will be obtained by replacing r is equal to, what is that, 4. So if I replace r is equal to 4, I will get a4 is equal to minus a2 by 8 into n plus 2, and a2 is given by this equation. So I will get a2 into 32 n plus 1 n plus 2 and so on. So now replace all these constants in the assumed equation y, that is y is equal to summation r from 0 to infinity ar x power k plus r equation. Before replacing that, we have to expand the equation like this. Y is equal to x power k a0 a1 x plus a2 x square and so on. If I replace all the constants in the equation, in this equation, and taking a0 common factor, I'll get the equation like y1 is equal to a0 x power n into 1 minus x square by 2 square n plus 1 plus x power 4 by 2 power 5 n plus 1 n plus 2 and so on. So this x power n is obtained since I'm doing the case for k is equal to plus n. I got this equation. I will call this one as y1 for the case 1. So for the case 2 is, I am going to replace k is equal to minus n. So in the same equation, just change the values of n is equal to minus n. So I will get y2 is equal to a0 x power minus n into 1 minus x square by 2 square minus of n plus 1 plus x power 4 by 2 power 5 minus n plus 1 minus n plus 2 and so on. So I can replace this complete thing as y1 and this one y2 like this. So the general solution will be y is equal to a y1 plus b y2, where a and b are arbitrary constants. So now we shall standardize the solution by choosing a0 is equal to 1 by 2 power n by gamma of n plus 1. So in the previous solution in y1 and y2, I am going to replace the value of a0 is equal to 1 by 2 power n gamma of n plus 1 only for the purpose of making the equation very standard here. So if I replace this value a0 in the y1 equation, I will get the equation like this: x by 2 whole power n 1 by gamma of n plus 1 minus x by 2 whole square 1 by n plus 1 into gamma of n plus 1 plus x by 2 whole power 4 1 by n plus 1 n plus 2 into gamma of n plus 1. So I'm just multiplying 1 by gamma of n plus 1 inside the bracket. So in the y1 equation, I'm taking all the values of 1 by gamma of n plus 1 inside. I'm combining that x power n by 2 power n as x by 2 whole power n. So I got this equation here like this. And also from the concept of gamma functions, we have gamma of n is equal to n minus 1 into gamma of n minus 1, and so I can write like gamma of n plus 1 into gamma of n plus 1, so n plus 1 into gamma of n plus 1 as gamma of n plus 2, n plus 1 n plus 2 into gamma of n plus 1 as gamma of n plus 3. So if I replace all this equation like this, I got the equation like y1 is equal to x by 2 whole power n minus 1 power 0 I'm taking, so the value will be equal to 1 only, and same thing here also, it will be equal to 1. So 1 by gamma of n plus 1 0 factorial x by 2 whole power 0 plus minus 1 whole power 1 gamma of n plus 2 1 factorial x by 2 whole square minus 1 square by gamma of n plus 3 by 2 factorial x by 2 whole power 4 plus so on. So now if I apply summation for this equation, I can write summation like this. I am keeping x by 2 whole power n here only. Summation r from 0 to infinity minus 1 power r gamma of n plus r plus 1 into r factorial x by 2 whole power 2r. So if I expand this summation with respect to r is equal to 0, 1, 2, 3, I will get the same equation again. So I'm taking this term 2 again inside only. So I'll get y1 is equal to summation r from 0 to infinity minus 1 power r x by 2 whole power n plus 2r into 1 by gamma of n plus r plus 1 into r factorial. Will get it. So now the function y1 is called Bessel function of the first kind of order n, and it can be denoted by Jn of x. So thus Jn of x will be given by summation r from 0 to infinity minus 1 power r x by 2 whole power n plus 2r by gamma of n plus r plus 1 into r factorial. So similarly for the next case, if I replace k is equal to minus n, I will get the equation like j minus n of x is equal to summation r from 0 to infinity minus 1 power r x by 2 whole power minus n plus 2r into 1 by gamma of minus n plus r plus 1 into r factorial. So hence the general solution of the Bessel equation will be given like y is equal to a into jn of x plus j plus b into j minus n of x is the series solution for the given Bessel's function in terms Bessel's differential equation by using Frobenius method. So in the next lecture I am going to discuss a few problems on the Bessel's differential equations. Thank you.